Welcome everyone to the Water Security Grand Challenges webinar series. This is the Wastewater Resource Recovery Prize webinar. Today, I have the privilege of introducing some really amazing winners for the Phase 1 for the Wastewater Resource Recovery Prize. So my name is William Gayak. I'm a Rice Fellow here at the Advanced Manufacturing Office at the U.S. Department of Energy, Office of Energy Efficiency and Renewable Energy. Briefly today, I'll give a quick introduction to the Water Security Grand Challenge, followed by a brief overview of the Wastewater Resource Recovery Prize by the prize manager. Then we'll have a panel of the Phase 1 winners speak. We'll allow time for audience questions for the first panel of speakers. Then we'll have a second panel of Phase 1 winners talk, followed by another round of question and answers that the audience can participate in. And then we'll wrap up essentially after that Q&A. If at any time you would like to ask a question, please use the question and answer feature to ask questions. So underneath that little white participants panelists area, you'll see a chat and Q&A feature. The seafoam green box highlights a Q&A section. So you can send your questions directly through that Q&A feature, type them in and send them. Alternatively, my colleague, Catherine Arsani is on the line, and so you can also directly message her questions, or you can send a question directly to all panelists, and we'll be able to ask your questions on your behalf. So the questions will be moderated and may be altered for clarity and simplicity. So briefly, the Water Security Grand Challenge. So the United States has historically benefited from access to low-cost water supplies, but challenges for freshwater supplies could threaten U.S. economic competitiveness and water security. The Water Security Grand Challenge is a White House-initiated, U.S. Department of Energy-led framework to advance technology and innovation to meet the global need for safe, secure, and affordable water. Using a coordinated suite of prizes, competitions, early-stage research and development, and other programs, the Grand Challenge has set the following goals for the United States to reach by 2030. Cost-competitive desalination technologies, transforming produced water from a waste to a resource, reducing water impacts at new and current thermoelectric power plants, doubling the resource recovery from municipal wastewater, which is what we'll be discussing today, and development of small modular energy water systems. For more information on the Water Security Grand Challenge and or to join our mailing lists, please visit us at the following web address or the following URL. You can also use your browser and your favorite search engine to find the Water Security Grand Challenge as well. I'm going to throw it over now to John Smigel, who has had extensive time in the Department of Energy working on prizes and research and development and evaluations. So with that, John, I am going to give you control if my computer allows me to.
Okay.
Just a second, I believe I have lost partial control from current slide. Apologies, I am having a little bit of technical difficulties. From current slide. Oh, weird. Apologies, just 1 second. My computer is not allowing me to pass keyboard control.
William, if you can't give me control, I can just say advance if that works.
Oh, yes, that's actually a good solution. So I apologize.
All right, that works for me. I don't mind. Okay, that's my ugly mug. Good afternoon, everybody. Thank you all for attending this webinar on resource recovery and DOE's Water Security Grant Challenge. My name is John Smeagol, and I'm with the Department of Energy's Advanced Manufacturing Office. I recognize what you're all really here to learn about is the more about the actual winning technologies from phase one of the prize. And because of this, I'm going to try to be as brief as possible, but as far as why I am going to be talking, go ahead, you can advance, William. I am the prize manager for this resource recovery portion of the Grand Challenge, which is, this one happens to be aimed at small and medium-sized facilities. And when I'm wearing another hat, I happen to manage the Industrial Assessment Center program for Advanced Manufacturing Office, which has been around for more than 40 years, and I've been managing it for more than 10 years. And that program is about helping the little guy. That's really what it gets down to. And as I said earlier, this program, this prize, is really aimed at small and medium-sized water facilities. Okay, go ahead and advance. Oh, I'm sorry, go back one, my apologies. There we go, okay. Let's see, there's an ongoing emphasis or paradigm shift within both the policymakers and water utility communities. This reflects a shift away from what is a fairly narrow focus on purely treatment, i.e., removing the bad stuff, to a more broadly defined resource recovery approach, extracting that which is beneficial from wastewater. Energy efficiency, or as we in the IAC program think of it, the most economical form of renewable energy, represents a huge potential opportunity for water facilities. And we see that within the IHC experience. And our stakeholders, such as EPRI and WRF, have reached similar conclusions as far as the amount of potential energy recovery. Beyond the embedded energy and the water resource itself, there are many potential beneficial materials, minerals, et cetera, resulting from the biological processes, nitrogen and phosphorus just being a few, that can be reclaimed and used elsewhere. This has been happening for some time to some extent, but its full potential has not been reached. And these potential resources will only increase as technology advances. Also bearing in mind that, with increasingly stringent water treatment requirements, costs are only going to increase and therefore enhance the opportunity for resource recovery. The opportunity space for resource recovery is only going to grow. Combined with inevitable aging of our water infrastructure, just reinforces the urgency to act now rather than waiting around. Next slide, please. Okay. Water Resource Recovery Prize, as you all know, is 2 phases. We've just completed the first one, and that's why you're all here. The first phase is really sort of a conceptual idea, a conceptual component. It's aimed at developing a library of solutions, 10 winners that can potentially be leveraged or replicated in other settings. Phase 2, which is just going underway here, is more of a demonstration of these technologies, providing a more enhanced menu of options aimed at reinforcing and capitalizing on previously discussed emerging trends within the industry. Okay, the prize is, as I said earlier, looking at small and medium-sized facilities, and this competition has been unique in that it's beyond a purely technology-based. Technology is the core of everything, but it's about expanding the technological feasibility outside the fence line of the facility itself. So we're talking about bringing teams in that represent all of the stakeholders in case of downstream demanders. We're talking about utilities. We're talking about agricultural interests. We're talking about municipalities, engineering firms, universities. All of these things were desired components or elements of this phase 1 competition. All right, next slide. And this is my last slide. As you all know, we're sort of right in terms of where we are. We're right at that junction there. We've gone through phase 1. COVID admittedly caused some delays in how we did this, but we're doing the best we can as far as that goes. So the timeline may be a little bit more delayed than what was originally envisioned, but right now, here we are in September, and we've passed that junction, and we're moving toward phase two. The phase two rules were released, I believe, on September 9th, and we're looking forward to a good process for the upcoming year. And at this point, I am going to turn it over, William, to whomever is next.
Thank you, John.
Much. Appreciate it.
Okay. Next up, we have Lauren Greenlee. I am finally able to pass over controls. Just one second. Okay.
Okay, I think I have control. Let's see.
Any luck?
No, neither with my mouse or keyboard. Huh.
Okay. Oh, wait, I think you now do.
Oh, no, I do. Okay, great. Great. Well, thanks. It's exciting to be here as a phase one winner and to talk about my team and the technology that we're focusing on. So our technology is an electrochemical technology where we're focused on recovering fertilizer from nutrients as well as fuel and energy and water. So the problem that we are focused on is the fact that in our current municipal wastewater facilities, phosphorus and nitrogen compounds come in the wastewater and are lost either to release to the environment or through removal because they've been considered as contaminants, really similar to what John was saying. So we really have spent the last few years thinking about sort of rethinking phosphorus and nitrogen as critical nutrients that we spend a lot of energy and money making into fertilizers, and then they're just lost to wastewater. So we're focused on the city of Norman in Oklahoma for our as our test case, and you can see in the slide I have a map here that kind of shows water consumption across the U.S. for energy production, and also areas in the U.S. that have a high water risk right now, and the city of Norman is in one of those areas. So a little bit more about Norman. So they are sort of an aging wastewater treatment plant that is looking to upgrade, and they're considered to be a medium-sized wastewater treatment facility in the central U.S. where there is a surplus of nutrients that would be good to be able to recover both phosphorus and nitrogen. And we see a lot of benefits for our potential technology, both in terms of water recovery and then also in terms of cost and energy savings. And I'll talk a little bit more about that in terms of the resources recovered. So our proposed technology would integrate with our partners' proposed indirect potable reuse upgrade to the Norman wastewater treatment facility. So the gray boxes at the top of the slide are the current treatment facility sort of summarized. And then the blue is indirect potable reuse, which our consulting engineering partner, Garver, is working on with Norman. And we would integrate our electrochemical technology within their indirect potable reuse system to try to recover phosphorus and nitrogen nutrients as a solid fertilizer product. Other significant benefits of our technology are that we also produce hydrogen, which can be recovered as a fuel during our electrochemical process. And because we use electrochemistry, we replace the need for chemicals addition for what typically happens in nutrient removal. So we're also reducing added salinity that's typically added to remove nitrogen and phosphorus in more traditional approaches, and we also reduce overall chemicals usage as a cost to the wastewater treatment plant. And certainly another huge benefit is that we're going to be enabling a huge recovery in treated water for indirect potable reuse for the city of Norman as a new a new drinking water source. And so this kind of shows a nice comparison of sort of state-of-the-art nutrient recovery or nutrient removal, I should say. So phosphorus removal is also often performed with ferric chloride, iron chloride coagulation. It's used to precipitate out, remove the phosphorus from the wastewater. And this is the process that adds salinity to the wastewater and also adds solid waste as an additional waste product from the wastewater treatment plant. And so what we're looking to do is the electrochemical approach, which has a benefit of no additional salinity added, and we're recovering a fertilizer called struvite, which is magnesium ammonium phosphate from our process. So just a little bit about our team. So I am the team lead. I'm co-founder and CTO of Catalyze H2O, which is a startup company that's looking at transitioning this technology out of our research lab. I'm also a professor at the University of Arkansas, and that's where we originally developed in the laboratory, lab scale, this technology. My co-founder for Catalyze is Shelby Foster. She's the CEO and will be leading business development and the market business plan. We are partnering with Mike Watts and Sean Skouras from Garver. They are consulting engineers, and they are directly involved with the City of Norman and their indirect potable reuse project there. And then we're also partnering with Chris Mattingly, who is the Director of Utilities for the City of Norman. And so we'll really be working closely with all team members for phase 2. And with that, a huge thank you for listening, and I look forward to any questions.
Thank you so much for that, Lauren. Next up, we have Casey McKinn from Crystal Clear Water Resources. I am about to assign you control.
Okay.
Let's see.
Okay, I have control.
Okay.
All right, good morning. My name is Casey McKinney, VP of Operations, and I'll be presenting today for Crystal Clear Water Resources. CCR is a veteran-managed company that was purpose-built in 2015 to address some of the most challenging issues related to wastewater treatment across multiple industries. We help companies fulfill the environmental aspect of their ESG standards by creating optimal solutions through leading-edge clean technology. CCR's proposal is in partnership with Ramona Municipal Water District, DUDEC, and Southern California Alliance of Publicly Owned Treatment Works, or SCAP. CCR proposes using our patented low-temperature distillation, or LT-DIST technology, to improve upon multiple aspects of the existing resource recovery process. Integrating our technology will increase the amount of recovered water available for reuse by nearly 100% and reduce the current disposal volumes by approximately 90%. This reduction in disposal will eliminate an estimated 17,000 truck miles per year, significantly reducing the risks and the environmental impact associated with the transportation of brine to the Point Loma ocean outfall. The San Vicente wastewater treatment plant currently utilizes reverse osmosis, or RO, as a component of their treatment process, which recovers approximately 550,000 gallons of reusable water per year. Integrating LT-DIST technology into the current treatment process will concentrate the existing RO waste stream, providing increased water recovery and decreased disposal volumes. This will result in lower disposal costs and lower greenhouse emissions from the disposal process. Our proposal also requires a microturbine generator to drive the thermal process, which will provide all the required electricity for the LT-DIST plant. Excess electricity can be used to augment a portion of the electrical demand from the existing treatment process. What differentiates the LT-DIST technology is that the phase change in the evaporation process occurs on billions of water droplets instead of tube bundles or membranes. With no phase change on metal surfaces, this virtually eliminates scaling and fouling risk within the plant. Additionally, the droplets in the condensation process allow for a more efficient heat transfer. Our technology operates under vacuum and is tolerant tolerant to fluctuating wastewater streams of up to 300,000 parts per million, requires little to no pretreatment, and operates efficiently under both full and partial load conditions. CCR's plants can utilize various heat sources ranging from conventional boiler systems to both low and high-grade waste heat to drive our thermal process. LTDIS is a step change technology from existing thermal distillation processes that promote seamless integration between other wastewater resource recovery facilities. Plant size can be scaled up or down to meet a facility's requirements. Our vertical design and lack of tube bundles allow for a significantly minimized footprint, making LTDIS ideal for smaller applications where space is restricted. The standardized and modular design allows operators to be familiar with the systems across multiple facilities. Our technology augments an already robust system by allowing standardization in maintenance, personnel training, and plant equipment and supplies. CCR can take existing RO waste streams and further concentrate them, dramatically reducing disposal requirements while increasing recoverable water. This application would be beneficial to other facilities utilizing RO as a component of their treatment process. While not economically viable at a location the size of the San Vicente facility, integrating our patented low temperature drying or LT dry technology with our LTDIS system, we can achieve zero liquid discharge or ZLD. Combining these two technologies eliminates the need for brine disposal, resulting in a full separation of water and solids and potential recovery of other valuable minerals for reuse. That concludes our presentation on LTDIS. I appreciate your time and attention. Listed below are ways you can contact and connect with us. If you have any questions, don't hesitate to reach out to us directly. Thank you again.
Thank you so much, Casey.
Thank you.
Our next speaker is Sebastian Tillmans from Codiga Resource Recovery Center at Stanford.
Good afternoon. As Ian said, I'm the Executive Director of the Codiga Resource Recovery Center at Stanford University. We are a pilot-scale testing facility for new technologies to recover resources from wastewater. And we have been partnering with two groups, Micromedia Filtration and Gate 5, as commercial vendors, and PRASA, the Puerto Rico Aqueduct and Sewer Authority, to develop this new system that I'll be talking to you about today. So you could please advance. So one of the key challenges that we are confronting in the wastewater treatment sector is that conventional activated sludge, which forms the backbone of most wastewater treatment processes, is just fundamentally inefficient. It consumes energy in order to essentially burn oxidized valuable organics. And it locks a lot of the remaining organics in hard-to-use biosolids. So that results in a common power consumption of about ½ kilowatt-hour per cubic meter of wastewater treated. And that translates to about 1 megawatt of power for a 12 MGD treatment plant, which is kind of our target size treatment plant for now. But one of the interesting things about this is that most of the materials in wastewater are actually fine particulates as opposed to dissolved materials. And that's important because biological treatment processes are very good at processing dissolved materials, not as good or not as fast at treating particulate materials. So if you advance to the next slide. So our approach that we're pioneering here is to really aggressively remove particulate matter from the wastewater upstream as soon as you can, essentially. Hence the name, get it fast, get it early. And we're relying on two processes to do that. The first is this process that you see on the left. That's called a microscreen. That's for wastewater professionals, that's a machine that looks very similar actually to a gravity belt thickener. But you use a screen that has a porosity. In our case, the porosity can vary, but up to 300 microns is typical. The water filters through the belt. You intercept the solids. They form a mat on the screen that promotes even greater filtration. And you can extract the solids and dewater them, whereas the water flows on to the next process, which is a continuously backwashed upflow media filter. So this, in this system, we have water flowing continuously up through a bed of sand, whereas the sand is constantly flowing down. This allows us to continuously clean the sand and achieve essentially optimal filtration constantly throughout the process. These sand filters were previously certified in the New York City watershed as achieving equivalency to microfiltration. So you can achieve a very high degree of filtration upstream of your process, which makes everything else simpler and more energy efficient. So to show it's kind of the full process flow diagram on the next slide of a typical treatment plant, you'd have your wastewater coming in with bar screens, grit removal, and then a primary clarifier, which achieves about 50% typical solids removal. So you're still sending a lot of solids into your biological treatment process that still need to be removed. By contrast, if you go to the next slide, the treatment process that we're proposing relies on a microscreen and then a primary filter, this advanced primary filter, to dramatically increase the amount of solids that are diverted and sent to solids handling. So this is important because your solids have energy value and resource value. And your liquids, in general, the highest value of the liquids is in the water. So after flowing through the primary filter, we have here a moving bed biological reactor that can operate much more efficiently than your typical biological treatment process because the solids are essentially gone. So you're using biological treatment to treat the soluble fraction of material, so you can achieve much smaller hydraulic retention times, much more rapid treatment. Following that is a tertiary filter that's the same kind of configuration as the primary filter and disinfection. But what's interesting about this configuration is by minimizing the amount of secondary biosolids that you produce, you dramatically improve the dewaterability of those solids, and you improve then the thermodynamics of energy recovery from those solids. So we can send the solids that we've separated from the wastewater, put them through an auger press to dewater them, a grinder, and then a flash dryer, after which we've created a dry powder that can be burned in a conventional solid fuel biomass burner to produce steam to drive a turbine, and the waste heat should be sufficient to drive the drying process, yielding excess production of process heat and electricity that are valuable resources. So if you can proceed to the next slide. So high-level punchline benefits of a system like this is that you could completely flip the energy balance of a treatment plant from being a substantial energy consumer to being a green power plant. For about a 12 MGD power plant, instead of consuming about a megawatt of power continuously, you would be exporting about 540 kilowatts to the grid. And with this technology, because the filtration allows you to dramatically reduce the size of any biological treatment, you can reduce the plant footprint by about 3/4, and you would reduce solids production by 96% because you'd be hauling off ash as opposed to a wet material that's mostly water. So the team that is helping to develop this approach, I'm participating as part of the Stanford Codica Resource Recovery Center. We have two private companies, Micromedia Filtration and Gate 5, and we're collaborating with the Puerto Rico Aqueducts and Sewer Authority, PRASA, to try and deploy this technology or test it in Puerto Rico. And I think that's the conclusion of my presentation.
Thank you so much for that, Sebastian. Next up, we have Jan Allen from Impact Bioenergy.
Hi, thank you. So I'm the CEO of Impact Bioenergy, professional civil environmental engineer, certified for quality and organizational excellence, and we also are the owner, operator, and beneficial resource manager for distributed anaerobic digesters. And let's advance to the next slide. Well, that's the cover the other way. So Impact Bioenergy has about 10 years of experience in applying traditional anaerobic digestion to small, distributed, in almost all cases, modular and prefabricated digestion systems. The focus has been on urban food waste, craft beverage manufacturing, food manufacturing, and now with this new project, with our phase one, we've pivoted back into the wastewater industry to merge our experience with other non-traditional feedstocks and look at co-digestion. So our skill set is to build modular, prefabricated, fast deployment digesters. We've managed to deliver them with cost effectiveness equal to large digesters. The capital cost for a single digester module, depending on which one you buy from us, would be between $150,000 and $1.5 million. And what this offers as a solution is lower cost, more control over your schedule, much more control over site civil and geotechnical issues, odor control, and organic product sale. So we're designing, with this particular project, we're designing for co-digestion of wastewater solids, fat, oil and grease, septage, and food waste. And this is an entirely zero waste system, and it's a zero discharge system. So the liquid that is discharged from the digester goes into beneficial use products in this particular case. And the net result is we're creating a circular local economy that really retains jobs, money, food supply, waste management, and renewable resources within a community. And in our particular project with this, we're in a much smaller community than some of the other applications. Let's go to the next slide. Our partner is Tenino, Washington. It's a town of 2,000 people. The wastewater flow is only 150,000 gallons per day. It's an MBR process. They have a lagoon storage system, and their effluent goes into a groundwater recharge system. So this is a very small community, but there are 16,000 POTWs in the United States, and only 1,400 of them now have digesters. So what is really driving our aspiration on this is bringing down the primary barrier to digesters being high capital costs for smaller to medium-sized facilities. Next slide, please. So the project that we advanced in phase one was called an Integrated Bioresource Recovery Project. And the objective is to prove cost effectiveness using a small to medium scale approach. We have two branded digester systems. The Horse is a smaller one, the Nautilus is a larger one. They're modular systems that serve between 500 and 30,000 people each. Impact has completed 14 of these systems, logging 130,000 operating hours, so we are in the commercial phase with this technology. The proof of concept is strong. We have zero odor complaints with 130,000 operating hours, and the labor input is very small. Proof of concept is also strong with the beneficial use of all the co-products. In many cases, regional digesters are looking at the digestate as an operating expense, and we are pushing that to a new paradigm where the organic output and the liquid becomes a commercially valuable product. The technology is suitable for co-digestion, meaning sludge, food, fog, and septage. And it's perfect for replicability because it's affordable and we can prefab these. They're easy to ship, easy to deploy. And in some cases, the install will be a one-day experience. Domestically, it's domestically invented, designed, and built and serviced. So this is a U.S. technology born in the Pacific Northwest, and we are now, we have facilities across the country with the 14 systems already deployed. Next slide, please. This just briefly, what this will do is take the existing treatment plant is in the dash box at the bottom. This will require a new receiving station for septage and food waste. It will go through feedstock preparation, go through a digester, and then we'll go into Class A solids after pasteurization, or PFRP. And the local county is also a partner in this because they have an economic development agricultural park next adjacent to the wastewater plant. So we're actually partnering with the city and the county. It is a net energy producer, which is part of the backup. But the energy is only half the story. The organic outputs are the other half. Next slide, please. This is a graphic of how this works. And one of the reasons we can do this is we are eliminating a tremendous amount of diesel fuel and trucking and transportation. All of this is done, it's co-located at the wastewater plant. And it also supports some of these local businesses. There are a number of cases where food manufacturing or beverage manufacturing is causing problems for existing wastewater infrastructure, and we're directly addressing that. Next slide. So one of the things that differentiates this from a more traditional approach is we are really focused on the outputs. We're delivering commercially feasible regenerative economy. The first photo at the bottom is we're going all the way to vehicle of biogas upgrading to CNG. We're fueling vehicles at the distributed digester, modular digester. We're also selling propane fuel substitute, which is really renewable biomethane. And then the organic products go out as a liquid, and then we dehydrate them and make a blended fertilizer. And in many cases, we're being integrated with a farming system to actually take the organic outputs from the digester and go right into food production on site. So it's beneficial use of all the resources that come out of the digester, and it simultaneously improves air, water, soil, climate change, job market, that we can touch all of these simultaneously. Plus, the community becomes more resilient and independently sustainable. Next slide, please. So, cost effectiveness. This is surprising, but we've been at this for 10 years trying to microscale digesters. It's a huge lift for us, but this does show that we compared our Nautilus, which is 1,500 wet tons a year, to the Hunts Point digester design report from 2010, and we are exactly the same capital cost per ton per year of input, which is how the metric we use. So this can be, the economy of scale argument really does not hold water, so to speak, when we deploy these systems. We're equal to the larger systems in benefit cost ratio. Next slide, please. So we're matching effective.
Apologies to interrupt, Jan. Just due to timing, I have to cut you off.
Okay.
I apologize for that. But yeah, please have a second to take a look at this slide, and then I think this may be the last one.
Yeah, that is. Thanks.
Oh. And then thank you so much again for your talk, Jan. Next, we have a brief Q&A from the audience that I believe, Catherine, were you going to lead?
Hi, yes. So right now I don't see any audience questions. So thank you very much, panelists. Great job. I'd like to remind the audience, though, if you have any questions, please feel free to put them in the Q&A box, even if you think of them later on throughout the presentation.
I have a general question for all the presenters while we're waiting on if any of the attendees have questions. There was some questions from other people that I heard that were following the prize that they were kind of wondering, like, how robust are these systems to seasonal changes with incoming wastewater? If anyone cares to, speak on that issue, if there's like much change in the types of waste stream that's coming in seasons, and if your system's able to handle those seasonal differences.
This is Sebastian chiming in on microscreens and advanced primary. From what I've seen in operating my facilities, I guess that what you would call the particle size distribution of the wastewater doesn't shift too much between summer and winter, for example, and it's more a temperature. The temperature, of course, changes, but so a physical chemical separation system like ours is not actually that. Isn't very much affected by by temperature, or should not be. But that's part of the things that I'm curious to investigate in this phase 1 part of the work.
Thank you for that, Sebastian. Would any of the other panelists like to answer?
Yeah, I could. This is Jan Allen. I can tell you on our project in the phase 1, our partner has a lagoon system, which is part of their wastewater treatment system, and that does serve as an equalization basin, so we can maintain a uniform flow rate and a uniform temperature, which we control pretty tightly on the digester. So having that existing lagoon system has really been a good way to optimize the digester.
Thank you for that, Jan. Would any of the other panelists like to chime in? Okay, I'm going to take silence as no, which is entirely okay.
Yeah, I guess Sebastian here. Another one nuance I'll add is, seasonality. One thing it does do is it can dilute the wastewater flows. If you get so certainly in California during the winter seasons, typically you have a lot more rain, and we hope to have a lot more rain, and that can dilute the wastewater. That can impact biological treatment processes in some ways and trigger kind of shifts in how the system behaves. Physical separation processes, again, you could leverage the fact that these systems are modular. You could potentially bring more modules online in the wintertime to compensate for higher flows. You would actually potentially have more flexibility if you're relying on a solid separation step, and it could protect your biological treatment process from some of those variations.
Thank you for that. At this time, do we have any more audience Q&A questions?
Nope.
Nope. I guess I could ask one more question if that's okay, and then we'll go on to the second panel. I was kind of curious, like, how specific are these systems for the regions or the locales that your systems are at, in terms of, in terms of how generalizable then would your systems be if they're not terribly specific to the unique wastewater streams that are coming into your wastewater recovery facilities, if that makes sense?
Yeah, I can start with that one. For ours, targeting phosphorus and nitrogen, that's in every single municipal wastewater influent. So we think that ours will be generalizable across the board. And in fact, we already see that there's really our commercial competitor is a chemical precipitation approach, and they've done demonstration plants around the U.S. So we think that our technology for recovering nutrients would be flexible in terms of any location.
Thank you, Lauren. Would any of the other panelists like to discuss that?
Sure. This is Casey with CCR. I would just say that our system is very tolerant to different feed water types, and so really we can scale up the size of our plant depending on what potential customer or client has as far as volumes.
Cool. Thank you, Casey. And then the last 30 seconds, would any other panelists like to jump on that question? Or
Sebastian here from Stanford. All municipal wastewater, there's a good amount of variation in different locations, but also broad similarities. And so this notion that the particulates are a problem and you benefit from separating them early on in the process is pretty consistent across the board. And so there's really an impetus to remove that material, extract it, harvest it early on in the process, and then that pays dividends for just about everything else.
thank you, Sebastian, and thank you again to all the panelists on the first panel. Next up, we have our second panel. And we have Alicia Holland and Jonathan Moreira from CarbonX, or if you can please correct me on the name.
That's right. Okay. I think we're ready to advance to the next slide.
Good afternoon, ladies and gentlemen. My name is Jonathan Moreira, and I'm the Technical Sales Director for CarbonX.
And my name is Alicia Holland, and I work in Research and Development here at CarbonX.
Thank you, Alicia. Let's begin with a short introduction to CarbonX. The company was established nearly 20 years ago with its primary focus being to aid coal-fired power plants achieve emissions compliance. CarbonX is a highly R&D focused manufacturer. We hold quite a few patents on our innovative technologies. I guess we need to advance the next slide.
He's advancing it.
Okay. Sorry, I forgot the time. So we hold quite a few patents on our innovative technologies. And although we're headquartered in Gainesville, Florida, we do have 3 manufacturing facilities that are spread from the Southeast to the Midwest. And that helps support our regional production and supply business model. To our knowledge, we're the only activated carbon pellet manufacturer in North America. Do you mind advancing the next slide? Thank you. With our headquarters in Florida, it's only natural that we take a keen interest in the ongoing water impairment catastrophe we've had here over the last few years with the blue-green algae blooms. And the primary driver for this ecological disaster is the discharge of excess nutrients, both phosphorus and nitrogen, to our local waterways. The source of this discharge includes, but not limited to, excess fertilizer, both from agricultural and residential sources, along with water and stormwater runoff. The nutrient loading of a body of water is one of the factors that we use to determine the health of the local ecosystem. Can you advance the next slide? Thank you. So to attack impairment of our local waterways, CarbonX has engineered a sorbent with enhanced phosphate sequestration capabilities. Its ability to both absorb phosphate in application and subsequently be recovered and reused as a soil amendment make this a doubly environmentally friendly solution. So advance the next slide, please. Thank you. The solution that we're talking about is HydroStore. So additional advantages of our HydroStore technology versus traditional biological treatments include a much smaller footprint for our treatment vessels, an improved ability to handle fluctuations in influent nutrient concentration, as was asked earlier about seasonal fluctuations and such, and a reduction in system head loss. Couple of these advantages with the copious other benefits throughout the media life cycle, you have a bona fide solution to excess nutrients. Alicia will now delve into the pilot testing and results.
William, can you please advance? Great. So again, my name is Alicia. I work in research and development at CarbonX, and I'm excited to present some early results on our partnership with using HydroStore with Braden River Utilities. So Braden River Utilities, or BRU, is a private utility that serves the Lakewood Ranch community in Southwest Florida, which straddles Sarasota and Manatee counties. So they're contracted to receive up to 19 million gallons per day, or MGD, of reclaimed wastewater from the cities of Sarasota and Bradenton, as well as from Manatee County. However, the water from Manatee County does not meet the Advanced Wastewater Treatment Standards, or AWT standards. So at scale, this project will process at least 1 MGD of non-AWT reclaimed water from Manatee County before storage and distribution at a construction cost of about $1 million. And this cost will be shared between BRU and the Southwest Florida Water Management District. Next slide, please. So we've had 2 phases of our pilot. So phase 1 ran in 2019 at low flow. So it's a very simple modular design where we monitor both the influent, which you can see in the graph at left in the green, and our effluent concentrations after the water has flowed through our bed. So you can see the influent concentration fluctuated between about 1 to 3 milligrams per liter, and the effluent concentration stayed well below the AWT limit of 1 milligram of phosphorus per liter. And again, that was under low flow. So we tried this again at higher flow, and this is ongoing now, and this is in 2020. So you can see again that we had fluctuations between about 1 and 4 milligrams of phosphorus per liter in our influent, but our effluent was able to meet or exceed our treatment objective of 1 milligram per liter of P, even under high flow. Next slide, please. You may be thinking, where can I fit this technology into my existing treatment plant? So I think that's half the magic. Our media does very well in modular vessels as well as in cast-in-place structures, and it is designed to be placed downstream of secondary treatment and upstream of disinfection, but this is highly customizable to suit your needs. Next slide, please. So Carbonex is currently pursuing pilots to gather additional performance data as well as to inform full-scale design, and our initial focus has been heavily trained on wastewater treatment plants. We've got 3 pilots identified. 1, the BRU phase 2 is underway, and 2 are under construction. But we're looking to expand our outreach to other markets, including stormwater runoff, sugar farms, food and beverage, and other industries. And I would like to note that we are aggressively seeking partners on pilots, as well as for ongoing commercialization efforts. Next slide, please. So if you have a phosphorus problem, please take down our information, and we look forward to hearing from you. Thank you.
Thank you.
That's all from us, William.
Thank you, Alicia. Thank you, Jonathan. I appreciate it.
Thank you.
Next up, we have Dan Spracklin from Somax Bioenergy.
Thank you, Will. Next slide, please. Today, I'd like to talk to you about or introduce you to the hydrothermal carbonization project at the borough of Phoenixville, located in suburban Philadelphia. Next slide, please. At Somax, we spent the last 8 years developing the HTC technology, and we've created partnerships not only with Villanova University School of Sustainable Engineering, but with the borough of Phoenixville as well. We brought together a team of industry and academia experts on biomass transformation and on wastewater treatment and resource recovery. Next slide, please. So the problem that we're identifying is not only with wastewater treatment, but in organic waste in general. The hundreds of millions of tons of organic waste that we produce every year as a nation have really 3 solutions to them existing. First one is landfilling. Second one is composting. And the third one is anaerobic digestion. Now, the problems with these existing solutions are that they're not very efficient and they require lots of land to process the material. As you can see, composting and anaerobic digestion are only 10 and 50% carbon efficiency. They're basically only recovering up to half of the carbon that's in the feedstock. And they take weeks to months to process the material. Next slide, please. So with hydrothermal carbonization, we solve these issues. HTC is a thermochemical process that mimics natural coal formation. But rather than hundreds of millions of years that Mother Nature takes, we accomplish this feat in as little as 30 minutes to 4 hours. We do this by applying mild heat, same thing you would 375 degrees Fahrenheit, same temperature you would bake cookies at, and mild pressure. This keeps the wet material in a pressurized state that actually breaks molecular bonds of the waste material so that we can actually separate out and recover all the elemental components of that waste material, regardless of what it is. Next slide, please. So our solution at Phoenixville is actually involves sewage sludge or biosolids and food waste. The borough will actually bring in additional food waste to pair with their sludge, and will process 16,000 tons of material per year. Some of the highlights of this project is that we are generating 10 times more electrical energy than the wastewater treatment plant consumes. We're creating 153% of the electrical demand of the wastewater treatment plant. That excess energy will be used within the borough to run borough facilities. It'll also run streetlights and stoplights. We'll get them to about 90% renewable energy and save them $1.8 million a year based on material that they were just throwing away. In addition to that, we have a carbon efficiency of 90%. We also have the lowest greenhouse gases emissions of any biomass conversion process. We're able to increase their solids handling capacity by 10x without increasing the plant footprint at all. And we're able to dewater the hydrochar material over 50% without any polymers. In addition, we're creating a pathogen-free sanitary products that eliminate or destroy pharmaceuticals, antibiotics, and PFOAs or forever chemicals. Next slide, please. So our baseline solution of products out of HTC are a hydrochar, which is a coal-like substance. It can be used directly as a soil amendment, and a liquid product that's a nutrient-rich process water that can be used as a fertilizer. Various post-treatments, both on the solid and the liquid side, allow us to extract additional nutrients in the form of ammonium sulfate, nutrient concentrate, and then provide distilled water. On the solid side, we can activate that hydrochar to become activated carbon. We can gasify it for renewable energy and ash, and then we can recover phosphorus from the solid component. Next slide, please. So beyond just power generation, what we're doing at Phoenixville, we have a variety of products that we can create from the solid side that act as a carbon sink. Everything from batteries and supercapacitors to activated carbons, graphenes, carbon nanotubes, in addition to sustainable building materials. Anything that's not used as energy acts as a carbon sink, allowing us to pull down carbon emissions from the atmosphere, or keep them out of the atmosphere, I should say, and sequester them for a long period of time. Doing this at scale has the ability to sequester gigatons of carbon every year. Next slide, please. So the HTC process is really a bolt-on process at any wastewater treatment plant. We intersect directly at the biosolids or the solid separation. So we don't interrupt the treatment plant process at all. We're not acting to go in front of any component. We're at the back end of the treatment plant. We put in our system to bolt on, and this not only functions at wastewater treatment plants, it can be installed at landfills, transfer station, anaerobic digestion plants, farms, or on compost facilities. So this would apply across the country at any wastewater treatment plant. We intersect at the point where you dewater your biosolids. Next slide, please. And with that, here's contact information. And thank you very much for your time.
Thank you for sharing, Dan. Next, we have Doug Hattler from 374 Water, Inc.
Thank you. Next slide, please. 374 Water, we are here to invent the future with us, or we want you to invent the future with us. We are looking at resource recovery with supercritical water oxidation. Next slide. 374 Water is a social impact clean tech company spun off Duke University out of Durham, North Carolina. We are commercializing a novel patent pending approach to supercritical water oxidation that was invented by its founders, Kobe Nagar and Mark DeSuze, with the support of the Bill and Melinda Gates Foundation and Duke University. Next slide. What we're trying to do with the supercritical water oxidative technology and with 374 Water is to really shift the paradigm from waste treatment to resource recovery. And as we've talked about, and as was mentioned earlier in the beginning, we're looking at recovering resources, but more importantly, we're also looking at decentralized modular waste treatment. We're finding, and I think we as a society are finding, that large centralized waste and wastewater treatment facilities may not be the most affordable and most effective way to handle our wastes. Next slide, please. So, as mentioned, if you look, a barrel of fecal waste contains about 87 kilowatts of energy, which is enough to power a Tesla SPU90. And as you see here, this is a picture of a developing country, and they're basically pouring all that energy off into the river, which one leads to environmental contamination, poor living conditions and health standards, but also we lose the opportunity to reuse that pent-up energy. Next slide. What we're looking at with the supercritical water oxidation is contributing to a circular economy where we can take wastewater and organic waste, put it through the system, generate clean water and electricity, minerals that can be reused, which can then be put back into the cycle for enhanced farming and food, as well as providing electricity back into our communities. Next slide. Supercritical water oxidation is an advanced oxidation methodology. It's a very compact treatment system that we've created. What you're looking at here is a 20-foot cargo container. That 20-foot cargo container can treat waste from 1,000 people per day. These systems are called NIC systems. They're one of the most compact wastewater recovery units in the world. What you see there on the vials, on the left side of it, you'll see the dark materials. That's the influent. On the right, you'll see effluent coming out of the unit. And this is clean water. The minerals or the materials that you see falling out of the bottom are minerals, mineral salts, which can be recycled or recovered and reused. Next slide. Supercritical water oxidation is taking advantage of the unique properties of water when it's raised past its supercritical point, which is above 374 degrees C, which is about 715 degrees Fahrenheit, and above 221 bar, which is roughly 3,200 psi. When you have organic waste with air as an oxygen source at that temperature in a reactor, the organics are fully soluble and miscible in the solution, and the oxygen is then able to essentially mineralize the organic materials and bring it down to just clean water and CO2. It's an exothermic reaction, so there is electricity that can be generated. That electricity is used to reheat the influent stream in the process, and in the larger units can be used to actually push electricity out to the site for reuse somewhere else on the location. We also can create heat, which can be used and recycled and reused for heat as well. And then we have minerals, which can be used for fertilizers and other things. The interesting thing is this all occurs in seconds within a reactor. We're finding that this is also very useful in destroying microplastics, contaminants such as PFAS. Next slide. Next slide, please. We have treated dewatered secondary sludge, primary sludge, waste-activated sludge, food waste, and we've done other waste such as motor oil, vegetable oil, landfill leachate, plastics, and industrial wastes. The feed streams generally are best when they're in 10 to 16% solids and there's caloric content in the material. Next slide. Right now, commercially, we're looking at creating 3 commercial units, the NIC 6, which would be 6 tons nominal per day, the NIC 30 at 30 tons per day, and the NIC 200 at 200 tons per day. We are currently operating, or Duke has a pilot unit, a NICS 1 operating at Durham, what we use for treatability demonstrations right now. If you look there on the right, you'll see for the NICS 30 and the NICS 200, we actually have the creation of the generation of electricity, which comes out of the reactors and then can be reused elsewhere. Next slide. The implementation of the SQO unit is very simple. It takes up very little space and can be put into an existing wastewater treatment plant process train. If it's going to be treating the biosolids and sludges, it can replace active aerobic digestion, and it can even replace and is looking to be more promising than thermal hydrolysis. It takes up a very small footprint, like I said, and can be placed anywhere on a waste source site. Next slide. I believe we have the next slide. There'll be a picture that shows the comparison of, if you look there, you'll see in the blue circle, these would be 3 SQO units, 3 NICS 30 units, which would replace all the items X'd out here and for being able to handle the biosolids. So you would save electricity from those units, reduce carbon dioxide generation from the electricity used, consumed in the use and the operation of those units, and then you'd see a significantly less footprint, and plus you'd be creating electricity as well. Next slide. That is 374 water. Thank you.
Thank you so much for that, Doug. Next, we have James Euler and John Willis from Genie Fuel Corporation.
Thank you, and good morning or good afternoon, depending where you are. Our presentation, I will present this. There's 2 partners shown here. Genie Fuel Corporation is commercializing the technology, and Brown and Caldwell is performing the site planning and integration with the utility. So next slide. Our process is called hydrothermal processing, and it works at the nexus of water, energy, and waste. So we take wet waste, we completely convert the organic content to renewable fuels, and we produce as an output clean, clear water. Next slide. The process is very similar to the way fossil fuels were formed, where you have wet organic matter, and over millions of years with temperature and pressure, you form liquid and gas hydrocarbons. We do the same thing exactly, but we do it in about 30 minutes. It's a hydrothermal process, wet and hot, 350 degrees C and 21 megapascal or 200 bar. And the conversion is complete as I described. Next slide. This technology was developed by the U.S. Department of Energy at the Pacific Northwest National Laboratory, and we've been partnering with them for more than 10 years to bring this to market. Next slide. This technology can be used with anything, essentially anything organic. Food waste, animal waste, chemical waste, pulp and wood, but we're focusing on wastewater solids, as you see in the upper left picture there. Next slide. The outputs of this are a biocrude oil, which looks just like petroleum crude, and a renewable natural gas, which is methane. The biocrude is refined at a refinery, conventional facility, into diesel, gasoline, and jet fuel, or any other product that a traditional refinery outputs. It works the same way. And the renewable natural gas can be put into a pipeline. Next slide. The particular project that we're working with for this prize is the city of Anacortes, Washington, which is right up in the northwest corner of Washington State. It's a utility of about serving about 17,000 people. Currently, Anacortes is using an incinerator to dispose of their wastewater solids. It's a fluidized bed incinerator, and the city wants and needs to replace this, and we'll be replacing it with a hydrothermal processing system. Our refining partner, because the biocrude oil, as I showed earlier, is refined, is Kern Oil and Refining in Bakersfield, California. One of the benefits of this refining step is that by producing renewable transportation fuels, these outputs are eligible for both federal and state programs which provide tradable credits, sometimes equaling more than the original cost of the fuel at the federal and state level. So those are all available with the fuels produced by our process. Next slide. Comparing this with the 2 processes that are directly involved, which is the fluidized bed incinerator, or it's called FBI in the middle column there. And then we've heard a lot about digestion, specifically anaerobic digestion or related biological systems. Compared to those, this GenaFuel hydrothermal processing system in the yellow box to the right produces a net energy benefit much greater even than the anaerobic digestion, and certainly better than the incinerator. And there are almost no residual biosolids left at all, and what is left is inorganic. It's phosphate, which we recover, and some sulfates. Next slide. So here are our two partners in this. Our third partner couldn't be on today, and you're welcome to contact either of us if you would like further information. And that's it. Thank you very much.
Thank you, James. Oh, wow. I didn't realize we were already at the end of our second panel. So we're now up for another audience Q&A. At this time, Catherine, I can't tell if there are any additional questions.
I don't see any. Presenters, you did a great job.
Yes. Yeah. Oh, I think I just saw one pop up. So there's a question for GenaFuel. What is the scale of the systems your process functions at? The audience question.
Yes, so it's highly scalable. We have built systems all the way from bench scale up to current systems that are being designed and constructed now are processing about 10 wet tons per day, and they can be scaled up further from that. It's highly scalable, and at this point we don't know what the upper end. We project it as somewhere between 50 and 100 wet tons per day per system, and then modules to go beyond that.
Thank you, James. And I'm actually going to throw that out to all the panelists on this panel, and I don't know if anybody from the first panel would like to answer that as well. That's actually a very good question. Like, what's the scale of your systems?
So this is Dan with SOMAS Bioenergy. Our base system is a shipping container. At the largest scale right now, it will process 16,000 tons per year. And at the smallest scale, we'll process 2,500 tons per year. But they are considered modular. So if you needed 32 tons per year, you just put in 2 reactors. So we number up rather than building a bigger box. But we can scale anywhere from 100,000 tons to 1 million tons a year, all the way down to 2,500 tons a year.
Yeah, this is Doug Hattler from 374 Water. We can scale from the equivalent of a 1 MGD, million gallon per day unit with a NICS 6, up to 30 million gallon per day wastewater treatment plant with a NICS 200. As the previous gentleman said, we also are modular, so you can put several of these working in parallel to give you more throughput.
Thank you. Would any of the other panelists like to answer, whether on this panel or from the last panel?
This is Sebastian here from Stanford, and with our project partners of Micromedia Filtration and Gate 5. The primary filters that we talked about for solids extraction from the wastewater start they kick in at about 500,000 gallons, about 500,000 gallons per day. And then they're modular technology, so you can scale up to essentially as large as you wanted to. The Gate 5 technology, which is the solids handling, both the drying and combustion and energy recovery, their minimum size is about 2.5 to 3 wet tons per day for a mix of primary sludge and waste activated sludge, or in our case, mostly the primary sludge. And then again, they could also scale up from there. So just like the previous panelists, you start with a unit that can handle a pretty small amount, and then you can number up relatively easily with a modular system.
Thank you, Sebastian. Would any of the other panelists like to answer before we move on to the next question?
Hi, this is Jonathan with CarbonX. Our technology is very similar to the other technologies that have been presented in the scalability as well. Currently, we have our BRU pilot project that we are running is projected to be up to a 1 MGD flow, but our technology could then be scaled up modularly as well we don't even have an upper bounds at this point, but as we commercialize, we'll obviously be able to put those numbers together a little better.
Thank you, Jonathan. I have another question that both Alicia and you kind of brought up and already answered, at least for your group. Are any of the teams currently looking for any partners or any collaborators for any aspects of their project or, I don't know, funding? Just out of curiosity, if this is of interest, since this would be an awesome venue to look for folks to partner with.
Well, this is Jim Euler from Genefuel. I suspect that I could give the same answer that most of us would, but as we enter commercialization, capital is always an issue, and the bigger the scale, the more you need. So partners in that respect are always something of great interest.
Thank you, James. Would any other...
Yes, this is Jan Allen with Impact Bioenergy. We right now, we are running a capital campaign on a platform called Fundable. And if you search Fundable, search Impact Bioenergy Inc. on Fundable, you can see our private placement offering. It's for accredited investors, but it really is crowdfunding. There's a pretty low minimum investment. And we are scaling up right now in a number of verticals. So it's that opportunity is out there on the street right now.
Thank you, Jan. It looks like we have time for maybe one more question. One of the attendees asks if the panelists can comment on the challenges and opportunities in developing markets for recovered resources. And this is open to both panels.
This is Jim Euler again from Genefuel. I think the technology is applicable to developing markets, but in many developing markets, you don't have centralized wastewater treatment plants in the same way as you do typically in North America, Western Europe, and some other countries. And so that presents a problem, but it can be solved by having much more decentralized systems, which are smaller and perhaps don't require the large centralized wastewater treatment plant.
Yeah, this is Doug Hattler from 374 Water. I agree with that. I'll also add that when you're bringing these technologies to market in the early stages, you're working from representations of the types of waste and wastewaters that you're going to be handling. There are regional differences in water quality, regional differences in the material, in the things that you encounter in the water and wastewater that you may be treating. So until you actually get a unit in the field working with the actual chemistry and physics of the waste that you're handling and the wastewater that you're handling, the materials that are coming out that you're looking for recovery could have slightly different specifications or slightly different compositions and chemistries, which then will have an effect on what specifications they can meet coming right out of the treatment unit. So it does require some understanding of the specifics of the materials that you're treating and coming in and what's actually going to be coming out, because chemistry everywhere, and it can vary and could vary, in the composition of the materials, particularly in places in the U.S., where you've got to deal with a lot of extra regulatory requirements that could tip a material into being treated as a hazardous waste if it's concentrated with things such like heavy metals.
Thank you, Doug. Would any of the other panelists like to speak? Maybe in the last 30 seconds, minute, we have time for this particular Q&A.
Sebastian, speaking here from Stanford. One of the things that, in my experience, has always been a challenge with resource recovery is the supply chain. So there's this something I've often heard is just because something has a lot of value doesn't mean it's worth anything, because you may not be able to find someone who's willing to pay for it. And that's, in some ways, what's really pushed me to focus on resources that are both readily recoverable and that have very clear markets. Energy is often underpriced in the United States, but everyone needs it. So there's a ready market for it just about everywhere. Same thing for heat, and that is the case also in low and middle income markets. So, something that motivates me a lot is that pound for pound, a kilogram of dry fecal material has more energy in a higher BTU value than a typical coal does. So there's a lot of energy value there, and that's something that's in short supply just about everywhere in the world.
Thank you so much for that, Sebastian. And with that, we're going to move from the Q&A. So thank you to all the panelists, to my colleague, Catherine, who has been manning the Q&A and who helped me a lot with the presentation. I greatly appreciate your time and efforts. To everyone, I thank all the attendees for joining us. I just wanted to reiterate that if you haven't heard about the Water Security Grand Challenge, or you may have only heard a little bit about it, go ahead and head to the Water Security Grand Challenge page and find out what's happening for our current events and join our mailing lists. Diana Bauer and Kevin Jane are the two co-leads for the Water Security Grand Challenge. Their information is available here. And with that, we conclude our webinar. Thank you so much for joining us today. Have a great week.